Hello all. In this lecture, I'll be discussing about asymptotic notations. So why do we need algorithm analysis? So algorithm analysis is to find the most efficient algorithm when you have so many choices. Here we have 5 approaches to algorithm analysis. The first one is step count, then we have operations count, asymptotic analysis, recurrence relations, and amortized analysis. In this lecture, we'll be discussing about the asymptotic analysis. Before understanding asymptotic notation, we should understand what is approximation and exact algorithms. Exact algorithm uses some kind of an exact formula to produce an exact value. This is not the case always. We have something called approximation algorithm, which produces an approximate solution or a value. Consider the Gauss summation, which is the summation of I is equal to 1 to n, which is the sum of n natural numbers. So it can be solved using the formula sum is equal to n into n plus 1 by 2, which is an exact formula and it produces an exact value as the result. Consider the approximation algorithm. The first approximation algorithm, it was used with the Turling formula for approximating factorial of n, where n factorial is equal to root of 2n pi n power n e power minus n. If this n is a very small number, then we may get an exact solution. But consider n is a very large number. Then in that case, obviously we may have to use some kind of an approximation formula to arrive at a closer, optimal solution. The second approximation algorithm was used to approximate the harmonic series. So here in the forthcoming session, we will be discussing the asymptotic notation to bring out some approximate solution with which we can identify which algorithm is better when you have multiple choices. So here we have the popular 6 asymptotic notations: big O, big omega, big theta, little o, little omega, and tilt. Asymptotic is a Greek word. It means approximation. Asymptotic notations is one of the approaches, and it uses the theory of approximation to identify a more relevant algorithm when you have lots of solutions. Here you can see a curve. Asymptote of this curve is a line, which is this dashed line, that closely approximates the curve but does not touch the curve at any point of time. Consider linear search. So here we have an array of numbers. It is not in any particular order. It's not in a sorted order. Now using linear search, say I want to search a particular value x. If x is 20, then in my first match itself, I will be finding the item. So this is called the best case because we find the item in one comparison. If x is equal to 45, then I will have to read each and every element, match it, understand that the item is not found until I read the last item. So this is called the worst case. If the item that I'm searching for is somewhere in between, then it is the average case. So you should first understand this before understanding what is asymptotic notations. Consider this graph. In your x-axis you have the input and in your y-axis you have the time. So you can consider any data set. So if the number of input, say number of purchases in a supermarket, if it keeps increasing over time, okay, over time, say a day, a month, a year, so this is the time and number of products purchased in a supermarket, say for example. So as the n increases, say this is the rate of growth of the purchase or the sales in time. Okay. So consider this function f of n, which is the rate of growth in time with n. As the input increases with time, your function is developing like this. Now, after a particular input n naught, you always see a curve which is always greater than the function f of n, which is denoted by c into g of n. So here, if f of n is less than or equal to, so this f of n is less than or equal to c into g of n, where n is always greater than n naught. So n is greater than n naught, a particular input. And c and n are real numbers, and c is always greater than 0, and n naught is greater than or equal to 1, because minimum there should be one input. And then you say that f of n is big O of g of n. That is, f of n is less than g of n. Let us understand it with an example. So consider f of n is equal to 3n plus 2 and g of n is n. Now, if f of n is equal to big O of g of n, then f of n is less than or equal to c into g of n, where c is greater than 0 and n naught is greater than or equal to 1. Now, if you substitute the values, instead of f of n, 3n plus 2 less than equal to c into, instead of g of n, we are substituting n. Now, by this equation, you can understand that you have 3 times n here, and if the value of c is anything above 3, then this equation will be satisfied. So say c is equal to 4. Then you can say that f of n is big O of g of n. So you can substitute and see 3n plus 2 less than or equal to 4n, where n is greater than or equal to 2 at c is equal to 4. Thus, you can say that f of n is the big O of g of n. This is big O notation. So, big omega notation. So, we have x-axis, which is n, which is the number of input, and the y-axis is time. Consider there is a function f of n, which is the rate of growth based on the inputs and time. You have the f of n growing at a particular pace. Now, if f of n is always greater than or equal to c into g of n, at a point where your n is greater than or equal to n naught, where n naught is greater than or equal to 1, and c is a value which is greater than 0, then you can say that this f of n, okay, so this f of n is big omega of g of n. So let us understand big omega notation with an example. Say f of n is 3n plus 2 and g of n is n. If f of n is equal to big omega of g of n, then we say that f of n is greater than or equal to c into g of n. Substituting the values, 3n plus 2 is greater than or equal to c into n. So here we have 3 times n, and we want the right hand side to be smaller, so obviously we can have the starting natural number c is 1. In that case, this equation will be satisfied. Therefore, you can say that f of n is big omega of g of n, which is 3n plus 2 is big omega of n. Let us take another example. So let f of n is equal to 3n plus 2 and g of n is equal to n square. Now, if you check, 3n plus 2 is equal to big omega of n square. So in that case, 3n plus 2 is greater than or equal to c into n square. So n square is a value which is always greater than n times. right? So whatever the scenario is, so you have to understand what is the order of n. Log n is always smaller than n. Log of log n is smaller than log n, and so on. So only if the condition satisfies, then you can say that f of n is big omega of g of n. The third notation is big theta notation. For a particular input n over a period of time, say there is a function f of n. Always, if you see c1 into g of n, which is always lower than f of n, and c2 into g of n always greater than f of n after a particular input n naught, then you call it f of n is big theta of g of n, where c1 into g of n is always lower than f of n and f of n is lower than c2 into g of n, where c1, c2 is always greater than 0 and n is greater than or equal to n naught, and n naught is always greater than or equal to 1. So this is the average case. Consider this example. F of n is equal to 3n plus 2 and g of n is equal to n. Now f of n is always less than or equal to c2 into g of n. So substituting the values, cn plus 2 is less than or equal to 4n, where c2 is 4. And f of n is greater than or equal to c1 into g of n, where using, see, if you equate this, you can understand that 3 times n is always greater than n, where c1 is 1. So in this case, you can say that f of n is big theta of g of n. Thank you.